Hi, Math 30-1s. Today what we're going to do is take a look at and study in depth what we call exponential functions. When we talk about exponential functions, the general form for an exponential function looks like this. Y is equal to a b to the exponent of x. Now, we've talked about this a little bit before. This exponent of x only belongs to the variable or the parameter b. Okay, so when we're doing a calculation, we're going to go b to the exponent of x first, and then multiply it to the a value. Now, when we are taking a look at exponential functions, we're going to have one of two scenarios. Okay, we are going to have either a growth or a decay function. Okay, a growth function means the graph is growing up and to the right as we move along the x-axis. A decay function is going to be coming down the other direction, so going down and to the right, okay, as we move or increase our x values. How we will know is dependent on the value of b in our equation. So when I have a growth function, this occurs when b is greater than 1. And when I have a decay function, that means my b value, okay, is between 0 and 1. So we really want to take a look at what b is in our equation. That'll determine whether our exponential function is growing or decaying. The value of a in our equation, okay, is usually your initial or starting amount in the question, or it is also actually the y-intercept, okay? So just some things to keep in mind as we are working our way through this lesson, and you'll see all of them come through again and again when we take a look at the questions and the examples. So to start, okay, we start talking about exponential growth. So it says, Mallory, a medical research scientist, discovered a new bacteria culture which could help strengthen a person's immune system. To find the growth rate, she isolated 5 cells of the culture and observed the following growth pattern. Okay, so they give the information to you both in a chart, which is just to the right of what I was reading there, and also just below in words. Okay, so when I take a look at that table of values, okay, remember that these will be our x values, our inputs, and these will be your y values or your outputs. In words, it says after 1 hour, there were 10 cells. Okay, so that piece of information is right here. After 2 hours, there were 20 cells. Okay, that's right here. And after 3 hours, there were 40 cells. Okay, so right here. So from the table of values there, I've got these points. I could say 0, 5, 110, 220, okay, and 3, 40. Okay, all pieces of information or coordinates that would exist on that exponential graph. Part A in the question now says, let t represent the time in hours and n of t represent the number of cells after t hours. The formula n of t as a function of time, t, can be written in this form. Okay, n of t is equal to a b to the exponent of t, which is basically your exponential function y equals a b to the exponent of x. And it says where a and b are constants and b has to be bigger than 0. Okay, so determine the values of a and b and write the function. So what I'm going to do is I would just take my general equation that they've given me, n of t is equal to a b to the exponent of x. Now what I'm going to do is I'm going to take some values from the table of values they've provided and substitute them into the equation. I'm actually going to start with the first set of points that they give me at time 0, okay, and you'll see why when I do the calculation here. When I substitute those values in, for n of t, I'm going to put 5. That's the y value. Then I'm going to go a b to the exponent of, and when y was 5, the x value is 0. Okay, and again, that just comes from the table of values. Now, the reason I do that, or I use that point, is because we know that anything to the exponent of 0 has a value of 1, even a variable. So now I have, in essence here, solved for a. So the value of a, okay, is 5. So now when I go back to my equation here, I can now write it like this. N of t is equal to, the a value is 5. I just solved for that. B to the exponent of x. All I have to do now is take another ordered pair from the table of values or from the write-up of the question and substitute those values in for x and y now, and I should be able to solve for b. So I'll just take the next set of ordered pairs there, 1, 10, substitute those values in and see what happens. So the y value, or n of t, would be 10. And that occurs when I have an x value of 1. Okay, and again, that's actually a nice calculation because b to the exponent of 1 is just b. So 10 divided by 5 is 2. So there's the value of b. Okay, and now I can therefore say, okay, my equation, n of t, will be equal to the a value was 5, and the b value was 2, and that is to the exponent of t. Okay, so there's our equation. Now, if you take a look back at what I had basically said at the beginning of the lesson, the a value, which was right here, was your initial or starting amount, like I said, and it was, right? You can see in the table of values, that was the starting amount that I had. The b value here tells you how much your graph is increasing by a number of times. So we would say it's doubling, okay, because that b value is 2. So I started with 5 and it's doubling, okay? That's what I'm multiplying by to get from one set of information to the next. B says, use the formula to determine how many cells there were after 8 hours. Well, 8 hours, okay, that's a t value, right? That's time. So when I go into my equation, it's going to be the number of cells after 8 hours will be equal to 5 and then 2 to the exponent of 8. Okay, so the number of cells after 8 hours, okay, will be 5 times 2 to the exponent of 8, okay? And remember, do 2 to the exponent of 8 first, then multiply by 5, and that will give me 1,280 cells. Okay, so there's our answer. Now, C says after 12 hours, there are 20,480 cells. How many hours did it take to have half of that amount? Well, remember that I was saying from the equation that 2 value there says that we're doubling, okay? So if I want to go backwards, that's halving. So really, half that amount would just be 1 hour later, wouldn't it, right? So 1 hour later, which would basically be 11 hours, okay? Because I'm doubling, if I do the opposite of that, which is halving, I half the 20,480, which would have been 1 hour previous, and again, that's 11 hours, okay? Now, D says, use your graphing calculator to graph this function, and this will represent exponential growth. So when I put this into my equation, so y is equal to 5 and then 2 to the exponent of x, what you will see, okay, is you will see a graph, okay, that looks very similar to this, okay? Comes through and increases up to the right. And again, I know it's going to be a growth function because my b value, okay, is bigger than 1. This is a real life scenario, okay, talking about cells, number of cells after a particular amount of time. So when I label the x and y axis, even though this is the graph that you get, I'm really only interested in what occurs in quadrant 1 because that's where the number of cells and time, okay, is positive. And if you remember from the beginning of the lesson, the a value in my equation tells me what the y-intercept is, so I know that this graph is hitting the y-axis or n of t axis there at a value of 5. So that's what the graph would look like. Okay, so that's an exponential growth example. Now, if I take a look at exponential decay, the example they give us reads like this. Chernobyl is a city in the former Soviet Union. In April 1986, there was a nuclear accident and the atmosphere was contaminated with quantities of a type of radioactive iodine. At the time of the explosion, the atmosphere was contaminated with 32,768 units of radioactive iodine. The following data was recorded for the dissipation of the radioactive iodine. So just like the first example, okay, they kind of give me information here, which again, if I really wanted to, I could organize it into a chart or a table of values. So you can see after 1 week, there were 16,384 units left in the atmosphere. After 2 weeks, there were 8,192 units. And after 3 weeks, okay, there were 4,096 units left in the atmosphere. When I take a look at the question, and they've started to write the equation right here, okay, in part A, again, there's my a value, okay, and again, that is the starting amount, okay, of radioactive iodine in the atmosphere, which they tell me in the write-up of the question. So that's what I started with. Now, if you take a look at all the values that follow after 1 week, after 2 weeks, after 3 weeks, they are half of the amount from the previous week. So that is my b value, okay? So I'm going to put 1/2 in here because that's what I'm doing to the values. I'm halving them, okay? If you want to use 0.5, that's obviously also okay. So my a value was 32,768, and my b value in this case is 1/2. Now, they say use the formula to determine how many units of radioactive iodine were left after 14 weeks. So I simply go into my equation, the number of units that are left after, okay, time is 14. And it's going to look like this, 32,768, and then 1/2 or 0.5 to the exponent of 14. Okay, so on your calculator again, 1/2 to the exponent of 14, take that value and multiply by 32,768, okay? And the number after 14 weeks is 2 units. That's what's left. Okay, so hopefully you're getting that in your calculator. Now, C says, use a graphing calculator to graph the function using the window shown. Okay, this is going to be an example of exponential decay. So again, they're nice to you telling you what your x, min, max, and scale are, as well as the y's. When I go and graph it, okay, you are going to see that your graph takes on this shape, okay, which is again a type of exponential decay. Okay, the values are getting smaller and smaller as I move to the right, or my x values are increasing. Again, when I label the axes, okay, this is the number and this is time. And just like the previous example, okay, this is a real life scenario, so I am actually only interested in the values that are going to occur in quadrant 1. And I should also know what this y-intercept is again. It is the a value in my equation, which is 32,768. Okay, so that's how I know where it is hitting the y-axis. Okay, again, remember the phrase that we always learn in math is, how do I find a y-intercept? Well, you let x equal 0. So when I go into the equation, t is your x in this case. So 1/2 to the exponent of 0 is 1 times the 32,768. Again, just 32,768. Okay. So just 2 examples of what the types of functions are going to look like. Now, moving on to the next page, what they do there is kind of talk about what I did at the very beginning of the lesson. Okay, they say that they give you the general equation or form of an exponential function, ab to the exponent of x. Okay, and just kind of telling you that's what we're going to be talking about in these lessons. Now, I'm going to compare 2 graphs here, 2 to the exponent of x and y equals 1/2 to the exponent of x. Now you'll see in the first question they say state the values for a and b. So I'll go 2 to the exponent of x over here and 1/2 to the exponent of x over here. So for this one, the a value is actually 1 and the b value is 2. For this equation, the a value is 1 and the b value is 1/2. Now, if you're confused as to how I'm getting 1, well, remember I told you early on the exponent only belongs to the b value. So up here, okay, the x only belongs to the 1/2, and here the x only belongs to the 1/2. That means there is a value of 1, which is actually in front of both of those equations, which is your a value, okay? So it's kind of hidden, even though you don't see it. They don't write it out, but the a value is 1 for both of those functions. Now B says, sketch the graph of the exponential functions for 2 to the exponent of x. Use the table of values and basically the grid. Okay, so when I talk about the first one here, 2 to the exponent of x, okay, the first x value they asked me to substitute into the equation is -3. So this is why we went over our exponent rules the other day. If I have 2 to the exponent of -3, okay, that's equivalent to 1 over 2 cubed, which gives me a value of 1 over 8. Okay, so when I have 3, I have 1 over 8 as the y value. When I substitute -2 in there, obviously it'll be 1 over 2 squared, so that's going to be 1 over 4. This will be 1/2. When I use 0, I get 1, okay, which is my y-intercept. When I put 1 in there, I get 2. 2 squared is 4. 2 cubed is 8. And 2 to the exponent of 4 is 16. So when I go and I graph these points, you can see -1, -2, -3, okay, extremely close. -2, it's at a quarter, okay, then 1/2, then at 1. At 1, I'm at 2. At 2, I have a y value of 4. At 3, 5, 6, 7, 8. Okay, and 4, 16 would be basically off the grid. So when I go and I draw that now, okay, your shape will look something like this, okay, up and through, and I will label that as 2 to the exponent of x. When I move down to the second part now, okay, they want me to graph or use the table of values which are associated with 1/2 to the exponent of x. So this time, when I use that x value of -3, okay, again, if you remember that from the previous day's notes, what I can do here is flip the value inside and make the exponent positive. Okay, so this is going to be 8. So when I use the value there, that's going to be 8. Okay, using the same process, I get 4 here, then 2, 1, 1/2, 1/4, 1 over 8, and 1 over 16. Okay, again, you'll see they share a y-intercept, the two graphs, at 1 there, at -3. Okay, I'm going to be up here at 8. At -2, I am at 4. -1, I'm at 2. Okay, and then I start getting a lot closer, okay, to the axes like so. Okay, so what happens is the graph will do this, come down, and it is decaying. And again, that b value, okay, is between 0 and 1. So you can see that I basically have a function that is decreasing as I move to the right. If you notice those b values, okay, 2 and 1 over 2, they're inverses of one another. When that occurs, you're going to see that the graphs are basically reflections of each other over the y-axis. Okay, so you can see that they are the same distance away, okay, being reflected over that y-axis. Okay. So some terminology now. It says an asymptote is a line whose distance from a given curve gets closer and closer to 0. In the above graphs, okay, the x-axis is a horizontal asymptote. Now, they're going to start to refer to that x-axis as an equation, okay, which is y is equal to 0. Okay, that's what the x-axis is, and it's a horizontal asymptote. Okay, so when you look up here, back on the graph, there's y is equal to 0, okay, the x-axis. So let's talk about these functions and just compare their characteristics. So the domain of the growth function, okay, remember that's the one that's going up in this direction, their growth function, 2 to the exponent of x. The domain, okay, can be anything associated with the real number system. The range of the function, y will be greater than 0. Notice I don't put or equal to 0, okay, because it doesn't touch that axis. It's always above it. So y is greater than 0. The x-intercept, there is none. It never touches or crosses the x-axis. The y-intercept is 1. And the equation of the asymptote, which in this case was the x-axis, and notice they say the equation, so I have to say y is equal to 0. You just can't say 0. You have to say y is equal to 0 when it's a horizontal asymptote. Okay. Now the decay function, okay, which is the one going down in this direction. Okay, again, the domain will be all real numbers, or an element of the real numbers. Same exact range. It never touches the x-axis. No x-intercepts, y-intercept of 1, and the same horizontal asymptote. So you can see they are identical, okay, in terms of those characteristics. So 2 to the exponent of x, again, is what we call a growth function. Okay, getting bigger as we move to the right, our x values are increasing. And 1/2 to the exponent of x is what we call a decay function, okay, getting smaller or decaying as we increase the x values, moving to the right. Okay, next page. Exploring the value of b. So this is basically what they're going to ask you is what happens when I change the value of b. Now, I've kind of alluded to this already in the lesson. The b value is basically your the rate at which the graph is increasing or decreasing. Okay, so that's what b is going to do. When you take a look at all of these functions here, okay, that they have given to me, the a value for all of them, okay, the a value for all of them is 1. And again, remember your a value is your y-intercept. So all of these graphs are going to go through the y-intercept of 1. That's why they've labeled it, okay, on the axis there. So all my graphs are going to go through that point, okay. So here's what happens. When I graph 3 to the exponent of x, okay, this one will be in blue, okay, it's going to look something like this, okay. I know it's going to be a growth function, okay, and it's going to go up and to the right like so. Okay, so I'll label this as 3 to the exponent of x, like so. Okay, now when I go and graph 10 to the exponent of x, okay, which I'll do in red here, the larger that b value, the faster that graph is going to increase. So again, it travels along that intercept and then it starts to really increase, okay, quite a bit more, okay, than 3 to the exponent of x. Okay, so it'll go up like this, and we'll say this is 10 to the exponent of x. So the rate at which it's increasing, okay, is much larger. When you take a look at 1 over 3 to the exponent of x, okay, which will be in black here, remember that that b value of 1/3, okay, is the reciprocal of 3. So that means it's going to be a reflection of 3 to the exponent of x over the y-axis. So it decays kind of at the same rate that 3 to the exponent of x was increasing. So I got to make sure when I graph this, okay, it kind of goes like this, down and decaying, okay, at the same approximate rate that it was increasing on the other side of the axis. So this will be 1 over 3 to the exponent of x. So when I go to now graph 1 over 10 to the exponent of x, okay, it's going to be a reflection of 10 to the exponent of x on the other side. So it decays at a very similar rate to which it was increasing on the other side of the axis. Okay, so something that looks very similar to this. Okay, so this would be 1 over 10 to the exponent of x. Okay, so hopefully that makes sense. So just some blanks to fill in here, okay, based on what we just learned there. When b is bigger than 1, so when your b value is bigger than 1, your curve is going to rise, or it rises more sharply as b increases. When your b value is between 0 and 1, the curve falls, okay, or decays more sharply as b decreases. Now, the next two examples here that they're taking a look at says, without using a calculator, make a sketch of first 5 to the exponent of x. Okay, well, first thing I know is that that's going to be a growth function because that b value is bigger than 1. So when I'm going to plot it on the axis here, or draw it on the axis, well, 5 is closer to 3 than it is to 10. So I know that when I grow it, it isn't a function. It's going to go through 1 here, okay, and it's going to be a little closer to 3 than it would be to 10, okay, in terms of the rate at which it is increasing. Okay, so hopefully that makes sense. 0.2 is kind of in hidden form because what I can do is I can actually write this as y is equal to 1 over 5 to the exponent of x. Okay, so 0.2 is the same as 1 over 5, and 1 over 5 is the reciprocal of 5. So I know that when I go and I graph that, okay, again, same thing, 1 over 5 is going to be closer to 1 over 3 than it is to 1 over 10. Okay, so it's going to look like this, okay, and down like so, okay, the rate at which it's decreasing. Now when I label it, okay, I'll label it as 0.2 to the exponent of x because that's what it was written like in the question, okay, but I can think of it as 1 over 5 to the exponent of x. D says you can verify all those on your calculator, so feel free, if you want to input those into your calculator to make sure that we've done them correctly, but I can tell you that we have. So to save you some time, you don't need to, but again, if you want to for peace of mind and so you can sleep soundly tonight, then by all means, okay, graph them on your calculator and you'll be able to see that. So just some general, okay, characteristics about graphs that take on this form, which is basically y equals b to the x because your a value is 1 for all of these graphs, okay? It says state the x-intercept for all of them. So what was the x-intercept? Well, there was none. Okay, none of those graphs cross or touch the x-axis. The y-intercept for all of these graphs was 1. The domain for all of those graphs was x is an element of the real numbers. The range for all those graphs was y is greater than 0. Okay, still an element of the real number system, but greater than 0. And the equation of the asymptote, and again, notice they say the horizontal asymptote is the x-axis, which is y is equal to 0. Okay. And again, I'll just write this beside it, so that's the more times we see it, hopefully, the better it sticks in our brains. Okay, moving on to the next page. So now finally, we take a look at what that value of a is going to do to the graph. Now, again, repeatedly, I've basically told you that that a value is what? It is our y-intercept. So when you take a look at these graphs, okay, you can see that in the first one, the a value is 1. In the second one, the a value is 2. In the third one, the a value is 5. Okay, and in the fourth one, the a value is 1/2 or 0.5. So that's going to be where all those graphs cross the y-axis. But you'll notice in all of them, the b values are all exactly the same. Okay, so b is equal to 3, b is equal to 3, b is equal to 3, and b is equal to 3. So what does that tell you? That tells you that they're all going to be basically increasing or growing at the same rate. It's just where they cross the y-axis that is different. Okay, so when I graph the first one, okay, in blue here, so 3 to the exponent of x, that one has a y-intercept of 1. Okay, and basically, okay, does something that looks like this, up and to the right. Okay, so there is your graph of 3 to the exponent of x. Okay, so like that. I'll graph the next one here in black. Okay, 2 times 3 to the exponent of x. So same growth rate, but this time going through a y-intercept of 2. Okay, so it'll appear to be a little higher. Okay, but grows or is increasing at the exact same rate. Okay, that the previous one was. So 2 and then 3 to the exponent of x, okay, like so. The next one here, okay, 5. So again, 1, 2, 3, 4, 5 up there. Okay, so that's where it's going to be crossing the axis. Okay, so it'll look kind of the same. Again, it appears to be higher. It's just that it hasn't gotten as close to the horizontal asymptote yet, but it will. Okay, and there's that graph. So 5 times 3 to the exponent of x. Okay, and then the last one, which I'll do this one in red as well because it's pretty low down here. 1/2 is the y-intercept, okay? So right there at 0.5, okay, this one will appear to be the closest to the axis at this point. Okay, and we just keep going up and growing at the same rate, okay, like so. So 0.5 and then 3 to the exponent of x. Okay, so again, just trying to make that connection between the a value and the y-intercept. Okay, B, just going to have us fill out the chart and basically take a look at that exact point. So first graph, 3 to the exponent of x, the a value was 1, the b value was 3, and guess what? The y-intercept was also 1. So here again, the connection between the a value and the y-intercept. Okay, value of a here was 2, the b value was 3, so guess what? The y-intercept is also 2. A value was 1, value of b is 3, y-intercept is 5, and then again 0.5 is the a value, the b value is 3, y-intercept of 0.5. So what is the effect on the graph of changing the value of a? Well, from our days of transformations, okay, we can say it's a vertical stretch, okay, about the x-axis. Okay, and also state that the y-intercept is equal to that a value. Okay. Now, in D, it says, if f of x is equal to 3 to the exponent of x, write the following in terms of the function f. Okay, so all you're going to be doing is every time you see a 3 to the exponent of x, okay, you're going to substitute with f of x because they're saying they are the same thing. So in the first one, I would just say y is equal to, and instead of 3 to the exponent of x, f of x. This will be y is equal to 2 times f of x, okay, because there's your f of x. This would be y is equal to 5 times f of x. Again, there's your f of x, 5 times that value, and equal to 0.5 okay, times f of x. Okay, and again, your f of x is your 3 to the exponent of x right there. In E, it says which transformations are associated with D, 2, 3, and 4. Okay, so in the second, third, and fourth examples that I just completed, what transformations are basically associated with those? So in the first one or the second one, okay, that was 2 times f of x. That would be a vertical stretch by a factor of 2. The third one, okay, would be a vertical stretch by a factor of 5. Okay, and the last one here would be a vertical stretch by a factor of 1/2, okay, or 0.5, okay. What is the effect of the parameter a? Okay, so what does a basically do to your graph? ab to the exponent of x. It's just always going to be, in this case, okay, a vertical stretch. So again, just kind of stating what it does as a generic case. Vertical stretch, and again, we'll say about the x-axis, which means closer to or away from the x-axis by a factor of a. Okay. State the y-intercept for each of the graphs. Well, again, just over and over again, the y-intercept is equal to whatever your a value is. Okay, and that's all that you need to write there. Okay, so some more characteristics and just things we want to make sure we understand before we move on here. It says the following summarizes the basic characteristics of the graph. So this would be like your notes section. Okay, anything you want to add in the columns or beside these points is great. Little diagrams, okay, those are great. But let's just see if we understand kind of what we've gone through so far today. So when I have an equation, which is in this form, y is equal to ab to the exponent of x, The y-intercept is going to be, okay, the a value. There is no x-intercept. Okay, these graphs do not cross or touch the x-axis. The x-axis is what we call a horizontal asymptote. Okay, the domain is going to be all real numbers, and the range is going to be, okay, again, greater than 0, okay, like so. Okay, now when a is bigger than 0, okay, so that's what we're talking about here. So when b is bigger than 1, we are going to be talking about a growth function, okay, getting larger as we go to the right. And when b is between 0 and 1, okay, we're going to have a decay function. The value of b affects the steepness of the graph as x increases. Okay, so as my x values are going further to the right. So when b is bigger than 1, the curve rises. Okay, goes up to the right sharply as b is increasing. And when b is between 0 and 1, the curve falls sharply as b decreases. Okay, so some points now where we're just going to select the correct response. The value of a affects the vertical stretch of the graph. Choose the correct alternative. So when a is bigger than 1, the stretch is an expansion. Okay, when a is between 0 and 1, the graph would be what we call a compression. Okay, and when a is less than 0, okay, which means it's going to be negative now, right? So remember, when something is less than 0, it's negative. So when a is, there's also going to be a reflection in the x-axis, okay? But that comes from transformations. Now, describe how the graph of the second function compares to the graph of the first. So this goes back to our transformations. Okay, so I'm starting with 4 to the exponent of x, and I end up with 2 times 4 to the exponent of x minus 2. So the two replacements that have occurred here are, okay, you would have replaced y with 1/2 of y, and you also would have replaced x with x minus 2. Okay, so again, doesn't matter the chapter that we're in, okay, or the type of function we're dealing with. As soon as I know those are the replacements, I can state that there has been a vertical stretch by a factor of 2. And I can also state that there has been a horizontal translation of 2 units to the right. Okay, so hopefully those still make sense to you from our transformation days. In B, again, I want to take a look at what all of the replacements are, or what that have occurred. So I would have replaced y with negative y. I would have replaced, we'll do stretches first, right? X with 1/5x. And I would have then replaced y with y plus 4, okay? Those are the 3 replacements that have occurred. When I replace y with negative y, okay, again, that is going to be a reflection in the x-axis. When I replace x with 1/5x, that's going to be a horizontal stretch. Okay, by a factor of 5. And then lastly, this will be a vertical translation. And this will be 4 units down. Okay, and there you go. Last one on this page here, okay. Explain, using transformations, why the graph of y equaling 1/3 to the exponent of x is a reflection in the y-axis of that graph. So the key here is that they're saying it's a reflection in the y-axis, okay? So as soon as I know something is a reflection in the y-axis, that means I should have been able to replace x with negative x, right? From transformations. That's how I reflect something in the y-axis. I'd replace x with negative x, okay? So what I'm going to do is I'm going to start with what they give me, which is y is equal to 1/3 to the exponent of x. Okay, that's what I start with. Now, I can rewrite 1/3 as 3 to the exponent of -1, right? That's what 1/3 is. Okay, and that's still to the exponent of x. Then, using my exponent laws, I would simplify that to 3 to the exponent of negative x, okay? So I started with 1 over 3 to the exponent of x, and I ended up with 3 to the exponent of negative x. I just rewrote it, okay, and simplified it in that form. Well, if I compare those two graphs, okay, so I'm actually starting with y is equal to 3 to the exponent of negative x, okay, and you're comparing it to y is equal to 3 to the x, okay, you can see comparing those two, x is replaced with negative x, okay, which is this right here, which means it is a reflection in the y-axis, okay, so there you go. Okay, last question here. Consider the function 4 to the exponent of x plus 2 and then minus 6. So without using a calculator, okay, determine what the domain and range of this function would be. So in order to understand this, okay, what we understand about exponential functions, okay, and in this case, you see your b value is bigger than 1. So you know it's going to be a growth function, okay, that this is what a growth function, okay, looks like in general. So in general, I have a domain that looks like this, and I have a range that looks like this. Okay, we've gone through that numerous times in this lesson. That's generally what happens with a growth function, right? But my equation here, oops, I apologize. Okay, my equation here, I'll get back, there we go, okay, has had a couple of transformations, okay? You can see that I would have replaced an x with x plus 2, and I would have replaced a y with y plus 6, okay? So that means my graph has moved 2 units left, and it has also moved 6 units down. Okay, now, if that's what happens, and I apply that to the red graph that I drew on the right, okay, well, what does that do to my domain? Well, it does nothing to my domain, okay? Even if I move that graph 2 units left, the domain is still going to be, okay, all real numbers. So that is unchanged. But if I take that graph and I move it 6 units down, remember your y-intercept here is at 1, move that 6 units down, okay, well, you know, what is your domain right now? It's y is greater than 0, right? So here is my horizontal asymptote. Normally, move that 6 units down. Well, that asymptote would now be, or mean, that your y values have to be greater than negative 6, right? Everything gets moved down 6 units. Okay, so there's your domain and range of that new graph. The y-intercept of the graph of the function is what they want us to figure out. So again, going back to what you learned very early on, especially probably, most likely in grade 10, that when you want to find a y-intercept, you let x equal 0, right? So y is equal to 4 to the exponent of, let x be 0, so x plus 2, then you're going to minus 6. So this will be y is equal to 4 to the exponent of 2, and then minus 6. So y will equal 16 minus 6. Okay, so y is equal to 10. Okay, so that's what your y-intercept is. Okay, your y-intercept has a value of 10. So it says the last part here, the equation of any asymptote of the graph of the function. Well, again, going back to the diagram I drew, right, my original y-intercept, horizontal asymptote is that y is equal to 0. So if I move everything down 6 units, right, 1, 2, 3, 4, 5, 6, there's negative 6. That's where the horizontal asymptote, okay, would be now. Everything gets moved down 6 units. So the equation of that asymptote now is y is equal to negative 6. Okay, so there's your new horizontal asymptote. All right, so lots to take in there, okay, in terms of growth functions, decay functions, a values, b values, y-intercepts, domain and range. Okay, so practice that. Again, any questions at any point, email me, and I will get back to you. I'm not sure if you guys are going to take a look at this lesson over the Easter weekend. If you do, that's great. If you do not, and you wait until after your evaluation on the previous unit, which is on Tuesday, then that's fine as well, okay? I'll keep posting some material, but you guys work through it at your own pace,